Kevin. So, Kevin, this morning I got a question for you.
Yeah, sure.
What
What
do
is
you
it,
know
Dr.
about
Hunter?
what do you know about formal charges?
Formal charges. Um, to be honest, I only remember most of what I know about formal charges from general chem from Chem 140. So, um, I'll try to best explain that about formal charges and how I think about them, how I tackle them in Lewis structures, and why they're kind of important in the, those Lewis structures. So,
Okay, let's see what you got.
all right. So if you look in Cengage and you look in the textbook online, there's this little section on formal charges. And the main takeaway for most students is going to be this equation that looks pretty large and kind of intimidating. You have brackets, number of valence electrons minus number of non-bonding electrons plus 1/2 number of bonding electrons. And so formal charge, you're given this formal equation, but I kind of have a more informal way of thinking and tackling formal charge in a problem. But you still need to know how to draw Lewis structures and what valence electrons are, and most importantly, how to read the periodic table for an element's number of valence electrons. And so we have group 1 is going to have 1 valence electron. Group 2 is going to have 2. If we're using the AB periodic table groupings, then this would be 3A, and 3A has 3 valence electrons, then 4, 5, 6, and 7 valence electrons. And so it's important to remember that valence electrons are the number of electrons on the outside are the outermost electrons in an energy level for that element. And so why is it important to still understand valence electrons and to know how to draw Lewis structures? Because that just sounds like this equation all over again. It doesn't seem like a shortcut, really. You're really still memorizing to be honest, you're still using this equation, but you don't have to go through these tedious calculations that the textbook is given. And this is from one of my other professors that I learned this from. And so I have this example over here, CH4 methane. I already drew out the Lewis structure. You can count the electrons if you'd like, but 4 electrons from 1 carbon, 4 electrons from 4 hydrogens, 8 electrons in total, 2, 4, 6, 8 electrons. And so with this correct Lewis structure for methane, if we were to do the calculations in the textbook, then we would have to go through a bunch of brackets. You have to throw in a half somewhere in that equation. And it can be kind of confusing and it can be kind of stressful, especially in an exam setting where you have a time crunch. And so what I learned was that formal charge is really how many electrons a specific element likes to have around it. And so that's basically just valence electrons, right? valence electrons are how many electrons an element likes in its outermost shell. And so it's sort of the same concept with formal charge. So if we look at the periodic table, we know that carbon has 4 valence electrons. 4 valence electrons. We know that in Lewis structures, every element except hydrogen has to have a complete octet. And so there are certainly 8 electrons around this carbon. But if you think about it, that each bond are shared electrons, 2 shared electrons, 1 here, 1 here. And this is for the sake of calculating formal charge a little bit easier. 1 here, 1 there, 1 here, 1 here, and then 1 here, 1 here. If I draw kind of a circle around the carbon, I got a little message on the bottom. Boy, oh boy. But you can see with this carbon, there seems to be 4 valence electrons, 4 outside electrons around the carbon. And by splitting this each bond in half, you can see that carbon sort of has 4 electrons that are always kind of around it. And that kind of relates back to the equation. It's sort of a shortcut. 1/2 the number of bonding electrons. Each bond that element has with another element, with another atom, it takes about 1 electron from that bond. And so if I were to do 4 minus 4, because we determined that each bond, on the carbon, the central atom, only has 1 electron from each bond, that would give us a formal charge of 0. Because that's the number of valence. Now I'm trying my best. Valence electrons, E- for electrons, and 4 for each of these. 1, 2, 3, 4. 4 minus 4, you get a formal charge of 0. And the opposite is also true, where hydrogen only takes 1 electron from that bond. Hydrogen from the periodic table has 1 valence electron. 1 minus 1, also 0. And so with bonds, you only count half of the electrons for each atom. For lone pairs, you just count the electrons. So if I were to do a quick example, if I can find space and move us right there, we have NH3, ammonia, and I'll just draw the Lewis structure. This is why knowing how to draw these are important. NH3, those are lone pairs. I'm doing my best. I I just draw those electrons right there. You would count 1, 2, 3, 4, and 5. You count that. Nitrogen from the periodic table is in group 5A, so 5 valence electrons. And then you would do 5 minus 5 is equal to 0. I, for some reason, can't write over there, but it equals 0. So it's nice to understand where this shortcut comes from, as it comes from the long equation. It derives from this equation on this in the textbook, but it just makes calculating formal charges a little bit easier. Would you like to add anything, Dr. Hunter?
Yeah, this is a perfectly nice way of calculating formal charge. It gets you there in a nice visual, pictorial way of looking at what's going on. The thing that I would add is it's not clear why we're doing formal charge. For instance, with simple Lewis structures like this, it's not clear that formal charge has gained us anything. But there are, we could do some complex ones here in a second that will show how using formal charge allows you to choose the best of two potential structures that might. And frankly, Kevin, I don't know whether or not the molecules know what their formal charge is. I think that they, I mean, I think it's our way of trying to understand what we see in nature and what we, a way of, certainly it's a way of teaching students how to come up with a way of understanding what we see in nature. But it's, I don't think the molecules care what their formal charge is. I don't think they're that sentient, right? So the molecules don't care. Why should we care? Well, we care because it helps us understand what we see. Should we do a little one that shows the formal charge really helping us to understand the structure a little better?
Yeah, sure.
Shall I do one? Okay, I'm going to do carbon dioxide. Okay, and we know the carbon is the central atom, so I'm going to put carbon in the center, and I'm going to put oxygen on either side. But I'm going to do it two different ways. I'm going to do carbon, oxygen, carbon, oxygen, and I'm going to do another one over here. And on this one, I'm going to put two double bonds. And on this one, I'm going to put a single bond and a triple bond. All right. And so if I think about all the electrons that I have available, I know that I've got so that's a potential Lewis structure for carbon dioxide, but this is also a potential Lewis structure for carbon dioxide. I've got 1, 2, 3, 4. I've got 8 bonding electrons over here on this other structure. I've got 2, 3, 4 times 2 makes 8 bonding electrons. On this one over here, I've got 2 lone pairs and 2 lone pairs, so I've got 4 lone pairs of electrons. Over here, I've got 2, 4, 6, 8. I've got 4 pairs of lone pairs of electrons. So these are both pretty similar structures. My carbon has 4 bonds. My carbon has 4 bonds. Here, my oxygen has 2 bonds and 2 bonds. Here, I've got 1 and 3. But those are pretty plausible. Here, I've got oxygen with an octet, 2, 4, 6, 8. 2, 4, 6, 8 for this oxygen. 2, 4, 6, 8 for this oxygen. 2, 4, 6, 8 for this oxygen. So those are both very plausible Lewis structures for carbon dioxide. However, if we look at the formal charge, and if we do it your way, we would probably take, I'd go something like this, and I'd draw, if I do it the Kevin Diaz way, I draw a circle around it right here, right? I draw 3 circles. Right? How am I doing? And I do the same thing. I do the same thing over here. This is not how I was going to do it, but we can do it this way.
Helps a little to visualize it, just like you said.
Sure. Okay. So carbon, 4 valence electrons, oxygen, 6 valence electrons. Very convenient that there's a little 6 up there above the oxygen. Very convenient that there's a 4 as in 14 above the carbon, if that helps. Okay, so we're looking at 4 and 6 valence electrons. Stop the screen here, come back here. All right, so here I've got 1, 2, 3, 4, 5, 6. 6 valence electrons minus 6 bonding electrons leaves a formal charge of 0 for that oxygen. For the carbon, 4 minus 1, 2, 3, 4 leaves 0. For this oxygen, the same as that oxygen, 0. But over here, I've got 1, 2, 3, 4, 5, 6, 7. It's 6 minus 7, formal charge of -1. That makes more sense because it's got more electrons. Right. Thanks, Kevin, for sorting me out on that one.
No problem.
I was so excited as I was going through that. So yes, that makes more sense. And so we've got carbon 1, 2, 3, 4. 4 minus 4, that I can do, equals 0. And 1, 2, 3, 4, 5. This one has 5, but 6 minus 5 is +1. There we go. Okay, so if we look at it this way, we say, okay, look at the formal charges here. They're minimized. The electrons are evenly distributed, and this gives us one possible Lewis structure. Over here, I have these two formal charges that exist inside the molecule, and so this structure over here is a little bit less favorable. So this is less favorable and more favorable. And so by using the formal charge mechanism, we can help to understand that this carbon dioxide with its double bonds, why that is more favorable, more prevalent than this version of carbon dioxide. And so formal charges helps us to get there.
Yep. I think formal charges are not as important as knowing how to draw a Lewis structure, but they certainly help you figure out the correct Lewis structure, and they're especially important for ions,
right?
Or polyatomic ions, because they're the exact reason why there is a charge on an ion in the first place.
Right. Do you want to do another one?
Yeah,
one with
sure.
ions? Okay. Shall we do the thiocyanate ion? So it's okay. So let's do. So thiocyanate is SCN, and overall it has a -1 charge. Okay. Can you see that all right?
Yep.
So thiocyanate, okay, I know I'm going to put my carbon in the middle, so I'm going to go, my possibility is SCN. In fact, I think I've got 3 possibilities. I've got one with like a, so I'm going to have one in the middle that has 2 double bonds here. I'm going to have one that's got a single and a triple bond. I have one that's got a triple bond and a single bond here. Okay. So those are 3 possible structures for the thiocyanate ion, right? We know that it's carbon in the center with a nitrogen and a sulfur on either side, but we don't know whether or not it's a single bond and a triple bond, or 2 double bonds, or a triple and a single bond on this way. Okay.
Mm-hmm.
So if I start putting some valence electrons around on those structures, Oh, I should make this bond a little longer. So this sulfur has an octet, an octet, an octet. That's promising, right? All these atoms like to have their octet. Here's a sulfur 1, 2, 3, 4, 5, 6, 7, 8. Carbon 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So everybody's got all the atoms have an octet in this middle structure, and 2, 4, 6, 8 for the sulfur, 2, 4, 6, 8 for the carbon, 2, 4, 6, 8 for the nitrogen. Really pretty promising, right?
Mm-hmm.
Okay, let's just quickly go to the periodic table again. Sulfur is in group 6, right below oxygen. So we've got 6 there, carbon in group 4, and nitrogen with 5 valence electrons. Okay, just so we remember those. So so if I do for my sulfur over here on the far left, I've got 6 minus minus 6, and oh, but look, it's got that 7th electron, minus 1. So 6 minus 7 gives us a minus 1 formal charge here. We've got 4 minus 4, no extra electrons, means the formal charge here is 0. We've got 5 electrons for its valence, minus 2 for the lone pair, sorry, minus 2, minus 3 for the bonding electrons gives us 0, right?
Yep.
And so then we do this sulfur, 6 minus 4 minus 2 gives us 0. Carbon has 4, so that's 4 minus 4 minus 0 gives us 0. And here is 5 minus 4 minus 2 gives us minus 1. And 6 minus 2 minus 5 gives us plus 1. And carbon again is 4 minus 0 gives us 0. And here we've got 5 valence electrons, minus 6 for the lone pairs, minus 1 for the bonding pair, gives us a minus 2. So if I look at this, I've got 3 choices. I've got a triple bond here and a single bond here between the sulfur and the carbon and the nitrogen. And if I do that, I have a formal charge overall where just the sulfur has a minus 1 charge. If I have my 2 double bond structure, I've got 2 zeros and a minus 1 charge on my nitrogen. Here in this third structure, I've got a plus 1 on my sulfur and a minus 2 on my nitrogen.
And I think for quick clarification, that sulfur on the right, its formal charge is correct. It's just 6 minus 2 minus 3, I believe, not minus 5.
Oh, right. 6 minus 2 minus 3. Sorry, I got excited there. Yeah, thanks for checking me out. Good thing you're here, Kevin, because otherwise I'd be making all sorts. Well, I'm making mistakes anyway. You're just correcting me. That's good. So 6 minus 2 minus 3 is plus 1, right? And so over here on this right-hand side, we've got much larger formal charges. And so you can imagine that internally to the molecule, hey, if we've got a positive side and a very negative side, that is going to result in some charge transfer across the molecule. And so this structure is much less favorable because it has larger formal charges. So one of the important rules that you can use for solving a structure using formal charges, if we've got significant formal charges or less significant, then we know that one of the less significant ones are favored. And so if we have plus 1 and minus 2, compared to 0 and -1, or -1 and 0, these two over here are more favored. And then in choosing between these two, we say, would we rather have the -1 on the sulfur or the -1 on the nitrogen? And if we have two elements, whichever is the most electronegative element, that will be the one that has the negative formal charge, if we have a choice between, if there's no other reason to choose. And nitrogen is higher electronegativity than sulfur, and so that means that our structure for thiocyanate is more likely this double bonded structure. And so for SCN-, it would be sulfur double bonded to carbon, double bonded to nitrogen. Overall minus, like that.
Yep. You just have to also recall that what electronegativity is, and it also makes sense for formal charges in this scenario, because it's just how much an element likes electrons, or how much they prefer to have electrons. And so with a negative formal charge, the higher electronegativity value, the more likely that atom's going to have the electrons, and that would verify a certain structure over a different Lewis structure.
Right. So if I'm looking at these two structures, and I say, which ones of my two elements, sulfur or nitrogen, is going to attract this -1 charge the best? Nitrogen attracts it more strongly. So it's more electronegative, and so it's going to be competing for this -1 formal charge, and that'll help us point to this being the correct structure.
Yep. All right then.
So that's our story on formal charges. Nice, Kevin. Thank you.
Thank you, Dr. Hunter.